Okay, so hello everyone. In this video, we will cover process synchronization and types of race condition. So in this video, first we will discuss process synchronization, then race condition, and then what is the solution for race condition, and then we will also discuss some types of race condition like producer consumer problem and printer spooler problem. So let's start with process synchronization. Process synchronization is a fundamental topic in operating system. When multiple processes run in our system, they can execute in two modes: serial mode or parallel mode. In serial mode, processes execute one by one. When one process starts, no other process can begin until the first one terminates. Think of it like an ATM machine. Customer use it one by one and nobody else can enter until the current person's transaction ends. In this scenario, there's no problem because one running process doesn't affect another. Modern systems use multi-programmed and time-sharing environment where we cannot guarantee only one process at a time. So multiple processes can run simultaneously, which creates challenges. So when many processes runs simultaneously, we categorize them into two types: cooperative processes and independent processes. So what is cooperative processes? Cooperative processes are those where the execution of one process affects another. This happens because they share something common. It could be variables, memory, a buffer code, or hardware resources like CPU, printer, or scanner. When processes share anything common, we call them cooperative processes, and their execution can affect each other. Now, what is independent processes? Independent processes are those where execution of one process doesn't affect another. There is nothing common in between. For example, if you are doing a transaction on SBI server while someone else is doing on transaction on HDFC server, these processes are independent processes running on different servers. So the key focus is on the cooperative processes because they can create problems if not properly synchronized. It's like giving a guitar to someone who doesn't know the music, then they will create only noise instead of music because the strings aren't synchronized. Now similarly, if cooperative processes aren't properly synchronized, they can lead to inconsistent states and deadlock that are difficult to resolve or impossible to resolve. So there is a condition called race condition. So let's examine a race condition through a simple example. We have two processes P1 and P2, like they are running on a system. Now what is the code for P1 and P2? Like they share something common. So let me introduce you first to the problem. What is the code here? Int shared equal to 5. Now in process P1, what is the code? Int x equal to shared x plus plus sleep 1 shared equal to x. So this is the code of P1. Now what is the code of P2? Int y equal to shared y minus minus sleep 1 and then shared is equal to y. So both processes share a variable called shared initialized with value 5. Now P1 has a local variable x and P2 has a local variable y. The key constraint is that we are working with the uniprocess system. We have only one CPU. So let's trace through the execution. Now the first is P1 gets CPU first and executes shared is equal to x. So x gets value 5. Now P1 executes x plus plus, so x becomes 6 and P1 executes sleep 1, causing the process to pause for 1 second. Now CPU switches to P2 because it cannot stay idle. So shared is what? Shared is equal to y, so y gets the value of 5. Now P2 executes y minus minus, so y becomes 4. Now P2 executes sleep 1, so pausing for 1 second. Now CPU will switch back to P1 now. P1 resumes and executes. Shared is equal to x, so shared becomes 6. Now P2 resumes and executes. Shared is equal to y, so shared becomes 4. So the final value is 4. But is it right or wrong? It is wrong because it should be 5 since we have added 1 and subtracted 1 from the original value. This incorrect result occurs because the processes aren't synchronized. Depending on the execution order, we might get 4 or 6 but never get correct answer of 5. Now this problem is called race condition. Different outcomes are racing to win and the result depend on timing rather than logic. So this is race condition. Now what is the solution for this race condition? It is critical section. A critical section is a part of program where shared resources are accessed by various processes. In concurrent systems with cooperative processes, every program can be divided into two sections: critical section and non-critical section. The critical section contains code that accesses shared variables, memory, or resources. The non-critical sections contains the code that's independent and doesn't involve shared resources. For example, if processes P1 and P2 both uses a count variable, the portions of code that manipulate this code variable belong in the critical section, while code working with independent variables like x, y in P1 and AB in P2, it will remain in non-critical section. The fundamental rule is if one process is executing in the critical section, no other process can enter the critical section simultaneously. This prevents race condition. To implement this, we add an entry section and exit section around the critical section. Now, what is entry section? Entry section is that code that process must execute before entering the critical section. What is exit section? Code executed when leaving the critical section. Think of it like a house with a lock. You must unlock to enter and lock when you have to leave. So this is what? This is entry section, exit section and critical section. Now, what are the conditions for synchronization? Any synchronization solution must satisfy our 4 conditions. The first 2 conditions are mandatory and the last 2 conditions are not optional, but like we can bear some error. So now first is mutual exclusion. If one process is in the critical section, no other process can enter the critical section. It's like a washroom. If someone is inside and has locked it, no one can else enter until they come out. The second condition is progress. Progress is what? This is mandatory condition. If the critical section is empty and a process want to enter, it should be allowed to enter without being blocked by other processes that aren't like interested in entering. No process should prevent other from processing, like when it's not even trying to use the critical section itself. Now moving forward to third condition. Third condition is secondary condition. We cannot say this is optional, but this is secondary. Bounded wait. A process waiting to enter the critical section should not wait infinite time. So while one process might use the critical section more frequent time rather than another, no process should be completely starved. For example, if P1 enters 10 times and P2 enters once, that's acceptable, but P1 shouldn't enter infinitely while P2 never gets a chance. This is what? This is condition of bounded wait. Now the other condition is no hardware, means no hardware or no speed assumptions. This condition is also secondary. The solution should be portable and not dependent on specific hardware configuration or processor speeds. It should work universally across different systems. The first 2 conditions are mandatory while the last 2 are desirable but not strictly required. Okay, now moving forward to the race problems. Types of race problems. What are the types of race problems? So the first problem is producer consumer problem. The producer consumer problem is like a classic example of process synchronization. We have 2 processes, a producer that create items and place them in the buffer, and a consumer that removes and process item from the buffer. Now both processes share a common buffer and a count variable that tracks the number of item in the buffer. So this is the code for producer, this is the code for consumer. In producer code we have int count is equal to 0. It is what? It is global shared variable in both the codes. Now void producer void int item p, it is what? Item p is what? Local variable. Now there is a condition, while true produce item p, while count is equal to n, means like if wait buffer is full, so there is a condition called while count is equal to n, means the n is what? N is the size of the items in the buffer. So this is the condition for buffer is full. Next line is buffer in item p, in is equal to in plus 1 mod n and count is equal to count plus 1. This is producer code. Now I will explain this code in detail also. Now what is consumer code? Void consumer void int item c, it is local variable, while true while count is equal to 0, means wait is buffer is empty, and item c is equal to buffer out is equal to out plus 1 mod n and count is equal to count minus 1 and consume item c. So this is the code of consumer code. This is written in C language. Now what is the case first? This is what? This is normal execution. In the best case, producer and consumer alternate properly, means producer produce item x1 and place it in the buffer 0. So count becomes 1 and in becomes 1. Consumer takes item x1 from buffer 0, count becomes 0 and out becomes 1. This is what? This is the normal execution. Now this works perfectly when processes are properly sequenced. Now what is the case 2? This is race condition, where the problem arises. Problems arise when both processes execute concurrently and access the count variable simultaneously. Let's say producer has produced 3 items x1, x2, x3. Now the count is what? Count is 3 and producer want to add x4 and start executing count is equal to count plus 1. Now the producer load count 3 into register rp and it increment to 4 in register. Now before like storing back it to the memory, producer gets preempted. Now consumer executed and loads count still 3, like count is still 3. Before storing back the memory, producer get preempted. So consumer executed the load count count, it is still 3 into register RC. Now consumer decrements it 2 in register and store back to the memory. Now producer resumes and store 4 to the memory. Now final count is 4, but it should be what? It should be 3, as we can see in the example also. If producer produced the one item and there will be x1, x2 and x4, then consumer consumed the item, then what its count should be? It count should be 3. What is the final count? It is 4. So this is wrong. Final count is 4, but it should be 3. So that is what? That is producer consumer problem. The issue occur because the instruction count equal to count plus 1 involves the 3 micro operation: load count from memory to register, increment register value and store register value back to the memory. If preemption occurs between these micro operation, race condition develops. So this is what? This is a producer consumer problem. Now we will see printer-spooler problem. The printer-spooler problem demonstrates process synchronization issues in a network environment with multiple users sharing a single printer. A spooler is a program that manages print jobs by storing them in the directory and sending them to the printer sequentially. When a process wants to print, it must execute this code. Now what is the code? Load m in RI. What is this? What is load next empty slot position? Now the second line is store file name, spooler directory RI. Now store file in that position. So increment RI, move to the next position, store RI, comma m in, update the empty slot pointer. So this is what? This is 4-line code that has to be executed when we have to print a file. Now in case first, this is single process. Process P1 want to print f1.doc. Now this will execute the code. So the first line is load in 0 into R1 and store f1.doc in spooler directory 0. Now increment R1 to 1, store 1 back to the in. So this is what? This is 4-line code as has been executed. Now this works correctly for single process execution. Now when multiple process race condition occurs, when process P1 and P2 both want to print simultaneously, initial state. Now what spooler contains? Spooler contains f1.doc, f2.doc, f3.doc and in equals to 3. Now P1 executes load in is equal to 3 and into R1, and P1 executes store f4.doc in spooler directory 3. Now P1 executes increment R1 to 4. Now P1 gets preempted before updating. Now before storing this value, P1 gets preempted. Now P2 executes load in still 3. It has to be 4, but it is still 3 because before storing P1 get preempted. So P2 executes load in is still 3 and into R2. Now P2 executes store f5.doc in spooler directory 3, like overwrites f4.doc. Now P2 executes increments R2 to 4. Now P2 executes store 4 to in. So f5.doc has been overwritten to f4.doc. Now P1 resumes after P2 executes store 4 to in. So the value is 4, but result is what? f4.doc is lost because f5.doc overwrote in position 3. This demonstrates data loss due to lack of synchronization. This is what problems we have seen in race condition. So that's it for this video. We will meet in next video. Until then, bye bye.